Welcome to another episode. Before we begin, take a moment to tell me where you're listening from and what time it is there. I always find it fascinating how one story can travel across so many places and hours, connecting people under the same sky. And if you haven't yet, you can subscribe to join this quiet corner of the universe, where science slows down and we simply listen. Now let's begin. Out there, beyond the reach of our eyes, galaxies are moving. Not gracefully floating in stillness, as we often imagine, but endlessly drifting toward one another. They stretch and twist, drawn by gravity's invisible pull, like dancers in a slow, inevitable embrace. And when they meet, they do something rather unsettling. They merge, they devour, they become one. Astronomers call it galactic cannibalism. It sounds almost grotesque, as if galaxies were living creatures swallowing one another whole. But in a sense, they are alive, in their own vast and patient way. Each galaxy is a cosmic organism made of hundreds of billions of stars, rivers of gas and dust, and a dark, unseen skeleton of matter that binds it all together. And like any living system, galaxies change. They grow, they die, they feed on others. To understand galactic cannibalism, we have to stretch our minds across timescales that defy imagination. A single collision can take hundreds of millions of years to unfold, too slow for any creature, planet, or civilization to witness from beginning to end. If we could speed up the universe, if we could watch the cosmos in fast motion, we would see a restless ocean of galaxies colliding, merging, consuming each other in an endless dance. What looks peaceful in a telescope snapshot is, in truth, the aftermath of violence. The term itself, galactic cannibalism, emerged in the late 20th century when astronomers began to notice strange stellar streams and warped spiral arms around large galaxies. These were the faint remains of smaller ones, torn apart and slowly absorbed. The universe, it seemed, had no respect for personal space. Take our own Milky Way, for example. It's not the serene pinwheel you see on postcards. It's an apex predator in slow motion. Right now, as you listen, it's in the process of consuming several dwarf galaxies that wandered too close, the most famous being the Sagittarius Dwarf. Over the past few billion years, the Milky Way has shredded it apart, stretching its stars into a long, ghostly arc that wraps around our galaxy like a forgotten ribbon. And it's not done yet. 4 billion years from now, a true cosmic banquet awaits. Our Milky Way will collide with the Andromeda Galaxy, another spiral teeming with hundreds of billions of stars. The two will merge into one, a new, enormous galaxy that astronomers have already named Milkomeda. It sounds like science fiction, but it's written in the quiet language of gravity. Every atom of that story is already in motion. The universe, at its heart, is a collector. It gathers, assembles, reshapes. Galactic cannibalism is not chaos. It's the mechanism of creation on the grandest scale. Each collision tears stars from their orbits, ignites new ones in bursts of brilliance, and feeds the monstrous black holes that lurk in galactic centers. In the aftermath, what remains is not ruin, but transformation. If we step back far enough, across the cosmic web, across the filaments of matter that stretch for billions of light years, we begin to see that this hunger is universal. Galaxies form, merge and merge again, building larger structures that eventually form clusters, and clusters that form superclusters. The pattern repeats endlessly, like fractals in motion, with gravity as the artist and time as the canvas. And so the universe grows by consuming itself. A paradox that feels strangely familiar. We, too, are made of remnants, the recycled dust of stars that once lived and died in earlier galaxies, long before ours was born. When you look up at the Milky Way, you are looking at something that has devoured countless worlds and may one day be devoured itself. It's humbling and a little haunting, but also beautiful. A reminder that even in destruction, there is creation, Every merger, every collision, every act of cosmic cannibalism leaves behind something new. A reshaped galaxy, a different sky, a new place for stars to burn. As we drift further into this story, we'll explore what galaxies really are, how they live, what they're made of, and why their appetite is written into the very laws of the universe. For now, just imagine the slowest storm imaginable. Galaxies twisting through space, drawn together not by malice, but by inevitability. An endless waltz of gravity and time, a universe that hungers, and in doing so, creates. When we look at a galaxy, we're not just seeing a cluster of stars, we're seeing an entire ecosystem. A galaxy is a city of light and gravity, an immense gravitational community bound together by forces that never sleep. Each one is a self-contained cosmos, a collection of hundreds of billions of stars, rivers of gas and dust, and something even stranger, a vast, invisible halo of dark matter that holds it all in place. If we could see a galaxy in its entirety, not just the parts that glow, we'd find that most of its mass isn't luminous at all. What our telescopes reveal, the shining stars and glowing nebulae, is only the surface glitter of a much larger structure. Wrapped around every galaxy is an invisible skeleton of dark matter, stretching far beyond the visible disk, like a ghostly scaffold made of gravity itself. No one has ever seen dark matter directly. It doesn't emit light or absorb it. It simply makes its presence known by the way it bends and pulls on the things we can see. Imagine a spiral galaxy, like our Milky Way. At its core lies a dense bulge filled with ancient stars, old, yellow, and quiet. Surrounding that core, the galaxy's disk spreads out in wide rotating arms of gas, dust, and younger, hotter stars, glowing blue and white. Between these arms are dark lanes of interstellar dust, regions so thick that they block visible light entirely, but still cradle the raw material for new stars. Within them, gravity works slowly, pulling atoms together until they ignite and shine. Beyond the luminous disk, the galaxy doesn't end. It fades into a diffuse halo of scattered stars and globular clusters, ancient spherical collections of stars that orbit like loyal satellites. And beyond that halo, invisible but dominant, lies the true mass of the galaxy, its dark matter envelope. Astronomers estimate that roughly 85% of all matter in the universe is dark matter. Without it, galaxies would simply fly apart, their visible components too light to hold themselves together. Dark matter is the silent architect of galactic form, and yet, what we can see remains staggering in scale. Take the Milky Way. It spans about 100,000 light-years across and contains somewhere around 200 to 400 billion stars. Each of those stars may host planets, moons, and entire systems of its own, and our galaxy is just one among at least 2 trillion others visible in the observable universe. 2 trillion islands of light, each one different, yet all built upon the same cosmic blueprint. But galaxies weren't always the majestic spirals and ellipticals we see today. In the early universe, not long after the Big Bang, around 13 billion years ago, matter began to clump together in small pockets under gravity's influence. These first structures were irregular, chaotic, full of gas and dark matter. Over time, they merged, collided, and grew into larger systems, the ancestors of modern galaxies. You can think of the universe as a vast sponge, a cosmic web, with galaxies forming along its filaments like dewdrops along the threads of an invisible net. Between those filaments lie enormous cosmic voids, regions so empty they make the word nothing feel inadequate. The cosmic web is one of the most beautiful patterns in nature, and it's real. Computer simulations like the Millennium Simulation and Illustris have shown this in astonishing detail, gravity pulling matter into strands and clusters over billions of years, shaping the universe into a structure that looks eerily like the neural network of a brain. If the universe had thoughts, they might run along these filaments. Galaxies rarely live in isolation. They gather in groups, clusters, and superclusters, enormous families bound together by mutual gravity. The Milky Way, for instance, belongs to the local group, a collection of about 80 galaxies, including Andromeda and a number of smaller dwarf companions. That local group itself is part of a larger cluster, the Virgo supercluster, which stretches over 100 million light-years. And even that is part of something grander, Laniakea, a supercluster so vast it contains hundreds of thousands of galaxies and spans over 500 million light-years. Within these immense structures, galaxies interact constantly. Their mutual gravity tugs at their shapes, distorting them, sometimes flinging stars into intergalactic space. These interactions are not rare, they're the rule. Every beautiful spiral galaxy you've seen is likely a survivor of countless encounters. Even the elegant symmetry of a spiral arm is a trace of gravitational influence, ripples left behind by passing galaxies or orbiting satellites. But to understand how we came to know all this, we need to rewind to a time when humanity didn't even realize that other galaxies existed. At the turn of the 20th century, the word galaxy meant only one thing: the Milky Way. Astronomers believed it was the entire universe. The faint smudges of light seen in telescopes, what we now call galaxies, were thought to be nebulae inside our own galaxy. The cosmos, it seemed, was small enough to fit in one mind. That changed dramatically in the 1920s, when a young astronomer named Edwin Hubble used the 100-inch Hooker telescope at Mount Wilson Observatory in California to study a fuzzy patch of light called the Andromeda Nebula. By measuring the brightness of certain stars known as Cepheid variables, he calculated their distance, and found that Andromeda was far beyond the boundaries of the Milky Way. It wasn't a nebula at all. It was an entirely separate galaxy, another island universe adrift in the dark. That discovery cracked open the boundaries of human imagination. The universe was no longer a single galaxy, but a vast ocean filled with billions of them. Hubble went on to classify galaxies by their shapes: spirals, ellipticals, and irregulars, creating the famous Hubble tuning fork diagram still used today. He also discovered something even more profound: that the light from distant galaxies was red-shifted, stretched to longer wavelengths, meaning they were moving away from us. This was the first evidence that the universe itself was expanding. Around the same time, Harlow Shapley, another pioneering astronomer, mapped the distribution of globular clusters in the sky. He found that they weren't centered around Earth, but around a point far from it, the true center of the Milky Way. In one generation, humanity lost its place at the center of the cosmos twice, first when Copernicus displaced Earth, and again when Hubble displaced our galaxy. The concept of galaxies as island universes was poetic, but also terrifying. Each one a realm so large that even light takes tens of thousands of years to cross it, and so numerous that no map could ever contain them all. Our universe, we realized, was not a peaceful expanse of stars, but a restless sea of gravitational islands, pulling, colliding, and reshaping one another in endless motion. And gravity, that quiet, patient force, is the unseen sculptor behind it all. It doesn't act with violence, at least not in our sense of the word. It persuades, it coaxes, it rearranges. Over millions of years, it can twist a spiral galaxy into an ellipse, fling stars into intergalactic exile, or pull entire clusters into cosmic embraces. In the language of physics, gravity is geometry, the bending of space and time itself. In the language of storytelling, it's destiny. Every galaxy, from the smallest dwarf to the grandest elliptical, is both the product and participant of this slow gravitational play. Their shapes, their rotations, their histories, all written by interactions that unfold too slowly for us to see. So when we look at the night sky and see the faint smudge of Andromeda, the nearest large galaxy to us, we're not just seeing another collection of stars. We're seeing a mirror of our own fate. Andromeda is moving toward the Milky Way at about 110 kilometers per second, roughly 68 miles per second, and in a few billion years, gravity will bring us together. The two galaxies will twist and tangle, their stars mixing like colors on a cosmic canvas. What begins as a meeting of two island universes will end as one, a new galaxy born from collision, shaped by the same invisible hands that built them. From the first faint glimmers of star formation to the grand clusters that span hundreds of millions of light years, galaxies are both the building blocks and the byproducts of cosmic evolution. They are the universe made visible, the places where matter, gravity, and time come together to create something luminous. And as we'll soon see, their collisions, their cannibalism, are not rare acts of violence, but fundamental steps in the growth of cosmic structure. Because in the end, galaxies are never truly separate. They are pieces of one vast gravitational web, drawn together by the same quiet force that once pulled the atoms of our bodies from the dust of dying stars. The same force that will one day pull our galaxy into another, and another still. The universe doesn't build in isolation. It builds through contact, through union, through appetite, and that's what makes galactic cannibalism so strangely poetic. It's not destruction at all, but the universe's way of remembering that everything is connected. Out in the silent darkness between galaxies, gravity writes a story that never truly ends. It's a story without sound, without light, a dance so slow that even eternity might blink and miss a step. From the outside, it seems peaceful. But the truth is, the universe is always in motion, and gravity is always at work, pulling, bending, persuading. Galaxies don't simply float through space like ships adrift on calm water. They orbit, interact, and influence one another, their trajectories warped by invisible tethers of mass. Every one of them, no matter how vast, is drawn toward others by a force that cannot be escaped, gravity, the sculptor of the cosmos. Imagine two galaxies separated by millions of light years, each one a swirling storm of stars, gas, and dark matter. Their outer halos reach far into the void, extending much farther than their luminous disks. These halos, faint and unseen, are the first to meet. It's not a collision in the way we picture it. It's more like an introduction, the brushing of invisible fingertips, a delicate gravitational handshake. Over time, hundreds of millions of years, that handshake becomes a pull. Each galaxy begins to feel the tug of the other. Their stars respond, not all at once, but gradually, orbit by orbit. At first, the effect is subtle. The edges of their spiral arms begin to warp, bending toward one another. Then, as the gravitational attraction strengthens, those arms stretch into long, graceful filaments, what astronomers call tidal tails. Tidal forces are the result of differential gravity, the same principle that causes ocean tides on Earth. The Moon pulls slightly harder on the side of our planet facing it than on the far side, creating a gentle bulge of water that moves as the Earth rotates. In galaxies, the same effect happens on a cosmic scale, except instead of water, it's stars, gas, and dust being stretched by the gravitational field of a neighbor. These forces can tear a galaxy apart, flinging vast streams of stars thousands of light years into space. Yet they also bind the galaxies closer together. With each pass, the two systems lose orbital energy through what's known as orbital decay, a gradual sinking of their paths as gravity robs them of momentum. Like two dancers drawing closer with every step, their movements become more entwined, more intimate, until eventually they can no longer remain separate. What happens next is one of the most majestic and violent acts in nature. The galaxies collide. But here's the strange part. Despite the name, it's not really a collision at all. Stars, though they may number in the hundreds of billions within a single galaxy, are so far apart that they almost never hit each other. The average distance between stars in a galaxy like the Milky Way is several light years, roughly 40 trillion kilometers, or about 25 trillion miles. That's like 2 grains of sand colliding only if they were placed several thousand kilometers apart. So when galaxies collide, their stars mostly pass through one another unharmed. What does collide are their gas clouds, their magnetic fields, and their gravitational structures. As these vast molecular clouds compress and slam together, new generations of stars are born in a frenzy of creation, a starburst event. In this way, a galactic collision isn't merely an act of destruction, it's also one of renewal. If we could watch it in fast motion, compressing 1 billion years into a few seconds, we'd see an astonishing ballet. 2 glowing spirals approach, their arms unfurling like ribbons in slow motion. Tidal tails stretch outward in arcs, some forming long streams of stars that drift away into intergalactic space, others curving back to merge into the growing core of the new galaxy. Bright waves of star formation ripple through the collision zone, lighting up like sparks in the darkness. And at the center, the supermassive black holes of both galaxies begin a slow inward spiral, a gravitational duet that will take eons to complete. This imagery, this dance of gravity, isn't poetic exaggeration. It's grounded in observation and simulation. In the 1970s, 2 astrophysicists, Alar and Juri Tuomre, brothers from Estonia, created some of the first computer models to simulate galaxy mergers. Their work was groundbreaking. At a time when computers had less processing power than a modern calculator, they managed to visualize the physics of galactic encounters using nothing more than simple particle simulations and a deep understanding of Newtonian gravity. The results were mesmerizing. In their animations, grainy, black and white sequences of dots representing stars, 2 disc-shaped galaxies approach, distort, and merge into a single amorphous mass. From these early experiments, the Tuomres demonstrated that the strange shapes of interacting galaxies observed through telescopes, the long tails, arcs, and bridges, could all be explained by gravity alone. No explosions, no magic, just mathematics and motion. One of their most famous examples, the antennae galaxies, NGC 4038 and NGC 4039, shows 2 galaxies mid-collision, their bright cores still distinct, but their spiral arms flung outward in spectacular arcs resembling insect antennae. Another, the mice galaxies, NGC 4676, appear caught mid-spin, their long tails stretching out tens of thousands of light years. These are not rare cases. The universe is full of such encounters, frozen in various stages of the dance. And thanks to modern simulations, far more detailed than those of the Tuomres, we can now watch entire galaxy clusters evolve. Supercomputers track billions of particles of gas, dust, and dark matter, each one obeying the laws of physics over billions of years. When you see one of these simulations, it's hard not to feel awe. Galaxies are not static jewels in space. They are rivers of motion, alive with turbulence and grace. One particularly striking feature of these cosmic dances is how the shape of each galaxy reveals its role in the encounter. Spiral galaxies, flat, rotating disks, are easily disturbed, their delicate arms stretching and twisting under tidal stress. Elliptical galaxies, by contrast, are more like dense clouds of stars without defined structure. When they merge, the result is typically another elliptical galaxy, smoother, rounder, and less organized. In fact, this process is how many of the universe's largest elliptical galaxies came to be. They are the ancient corpses of once spiral galaxies, that long ago collided and merged, their ordered motion erased by the chaos of gravity. Over time, the newly formed galaxy settles into equilibrium. Its stars orbit within a new gravitational potential, its shape gradually smoothing out as the remnants of the merger disperse. The tidal tails, those magnificent ribbons of light, fade into faint stellar streams, barely visible even with powerful telescopes. But they never truly disappear. They remain as fossils of motion, whispering the story of what once was. Even now, telescopes like Hubble and James Webb capture galaxies caught mid-collision, cosmic love stories frozen across millions of light years. Some, like the Whirlpool Galaxy, M51, show companion galaxies tugging on their spiral arms, triggering bursts of new stars that glow like embers. Others, like Centaurus A, display the scars of a recent meal, dust lanes twisted across a giant elliptical core, the remnants of a devoured spiral galaxy. When astronomers study these mergers, they see more than beauty. They see the machinery of cosmic evolution at work. Galactic collisions are one of the primary ways the universe recycles itself. They redistribute matter, reshape dark matter halos, and feed the supermassive black holes that lie at every galaxy's center. In a sense, the universe grows through its own acts of consumption. And though the process may sound violent, it's remarkably elegant. No explosions in the Hollywood sense, just the slow, precise unfolding of physics. Gravity pulls, momentum resists, time does the rest. It's humbling to realize that while galaxies move at incredible speeds, hundreds of kilometers per second, hundreds of miles per second, their interactions still unfold over billions of years. From our tiny perspective, it's imperceptible, the same way we can't see the motion of continents, or the slow erosion of mountains, we can't sense the motion of galaxies. But in the vastness of time, everything dances. The Toomri brothers once described galactic mergers as the natural choreography of gravity, and they were right. Every encounter, every spiral, every tail of stars stretching into the void, all of it is written by the same universal law. Gravity is not merely a force, it's the rhythm that keeps the cosmos in motion. When you look at an image of colliding galaxies, remember that what you're seeing is time stretched thin, a single frame in a dance that will outlast every star you've ever known. Somewhere out there right now, two galaxies are beginning to draw together. They'll meet, merge, and form something entirely new. And long after their stars have burned out, the memory of that meeting will remain, etched into the structure of the universe itself. So the next time you see a galaxy through a telescope or in a photograph, don't imagine stillness. Imagine motion, the slow turning of billions of suns, the unseen pull of gravity shaping destinies across light years. Every galaxy is a dancer in this vast cosmic waltz, gliding to a rhythm we can only just perceive. A dance choreographed not by chance, but by the quiet persistence of gravity, the universe's oldest and most patient composer. When galaxies meet, the universe takes a breath, not a sudden, explosive gasp, but a deep, drawn-out inhale that lasts hundreds of millions of years. Across unimaginable distances, two colossal systems of stars, gas, dust, and dark matter converge. And what follows is both chaos and creation, violence and beauty, the kind of event that reshapes the very structure of the cosmos. Galactic collisions are not accidents. They're the inevitable result of gravity's long game. Every galaxy is surrounded by a vast halo of dark matter that extends far beyond its visible edge, an invisible bubble of gravity. When two such bubbles overlap, the galaxies inside them are pulled into a slow spiral toward one another. Their orbits decay over time, tightening as friction from gas clouds and tidal interactions saps away energy. What begins as a gentle pull across millions of light years becomes a cosmic embrace that cannot be undone. The first sign of contact is distortion. One galaxy begins to stretch the other, tugging at its outer arms, drawing long streams of stars outward. These spectacular structures are called tidal tails, immense arcs of light that can extend for hundreds of thousands of light years. They are like the splash of cosmic surf, the visible imprint of invisible gravity. Sometimes the collision forms bridges of material connecting the galaxies, tenuous links of stars and gas spanning the void between them. Astronomers have photographed these intergalactic bridges glowing faintly, like strands of silk stretched across space. In other cases, the gravitational encounter can fling entire clusters of stars far beyond their parent galaxies, leaving them adrift in intergalactic space. One of the best examples of this is the antennae galaxies, a pair of colliding spirals located about 45 million light-years away in the constellation Corvus. They are locked in the midst of a merger, their disks overlapping, their cores swirling toward one another. The name comes from the two enormous tidal tails that sweep outward in arcs resembling insect antennae, each one a stream of millions of stars flung into the void. What's astonishing is what's happening at their centers, a storm of star formation. When galaxies collide, it's their gas that takes the brunt of the impact. While stars pass by each other almost undisturbed, clouds of interstellar gas slam together. The collision compresses the gas, increasing its density and pressure until it collapses under its own gravity. In those collapsing pockets, new stars ignite in brilliant bursts. Astronomers call this a starburst, a period when a galaxy forms stars at a rate hundreds of times faster than normal. In the antennae galaxies, the starburst regions shine so brightly that they dominate the infrared spectrum, glowing with the heat of millions of newborn stars. These regions are often hidden by thick dust, so astronomers observe them with infrared and radio telescopes, peering through the smoke of creation. It's a paradox that never loses its wonder. Collisions that destroy galactic structure also give birth to light. Destruction begets creation, the universe's favorite pattern. Another spectacular example is the Mice galaxies, NGC 4676, located about 290 million light-years away in the constellation Coma Berenices. They're named for their long, thin tails of stars and gas, stretched out by mutual gravity like streamers unfurling behind two dancers mid-spin. The Mice are currently in the early stages of their merger. They've already passed close enough to distort each other dramatically, but not yet close enough to fully combine. In a few 100 million years, they'll complete the dance, fusing into a single, larger galaxy. Then there's the Tadpole Galaxy, UGC 10214, around 420 million light-years away in Draco. It gets its name from its extraordinary shape, a small, bright head with an enormous, thin tail of stars stretching nearly 280,000 light-years behind it. This is a classic snapshot of galactic cannibalism in action. A smaller intruder galaxy passed close to the tadpole, pulling stars outward into that shimmering tail while being devoured in the process. Through telescopes like Hubble, you can even see clusters of newly formed blue stars sparkling along the length of that tail, stars that didn't exist before the collision. These examples are more than celestial art. They're proof of how the universe builds complexity. Every time galaxies collide, the shockwaves compress clouds of hydrogen, triggering waves of star formation that ripple through the system. The gas doesn't just collapse randomly. It forms in clusters, vast nurseries where thousands of stars are born together. Some of these young stars will explode as supernovae within a few million years, seeding the surrounding space with heavier elements like carbon, oxygen, and iron, the raw materials for planets and eventually life. So when two galaxies collide, they're not simply wrecking each other, they're enriching the cosmos. Each encounter stirs the ingredients of future worlds. Our own sun, and the elements in our bodies were forged in galaxies that once collided long before the Milky Way took shape. In a very real sense, we are the descendants of ancient cosmic collisions, but not everything that happens during a galactic merger is nurturing. The violence runs deep, especially in the hearts of galaxies, where supermassive black holes lurk. Nearly every large galaxy harbors one at its core, with masses millions or even billions of times greater than the Sun. When two galaxies merge, their black holes begin a slow gravitational dance of their own. At first, they orbit within the chaotic core of the merging system, gradually drawing closer as friction with gas and stars robs them of momentum. Over millions of years, they spiral inward, forming a binary black hole system, two invisible giants locked in orbit. As they get closer, they begin to radiate energy in the form of gravitational waves, ripples in the fabric of space-time itself. This process is so subtle that it took until the 21st century to detect it directly. The first confirmed gravitational waves, observed by LIGO in 2015, came from much smaller black holes. But in 2023, astronomers using the Nanograv project reported evidence of a gravitational wave background, a cosmic hum likely caused by the merging of supermassive black holes across the universe. Every galactic collision contributes to that symphony, a deep, low-frequency rhythm that fills all of space. When the two black holes finally meet, the energy released is staggering. They merge into one, releasing more power in a brief moment than all the stars in the observable universe combined. And yet, no light escapes. Only space itself ripples. As this merger unfolds, shockwaves ripple through the surrounding gas, heating it to millions of degrees. Jets of high-energy particles can erupt from the galaxy's core, blasting out into space for hundreds of thousands of light-years. These phenomena, active galactic nuclei and quasars, are among the brightest objects in the universe, powered by matter falling into the black hole at near-light speeds. So even in the darkest centers of galaxies, the collision becomes a spectacle of radiant energy. Over time, the two merging galaxies lose their distinct shapes. Their spiral arms dissolve into clouds of stars and dust, their disks collapse, and their black holes settle into a common core. The result is usually a massive elliptical galaxy, smoother, redder, and quieter than the lively spirals that came before. The chaos subsides. Star formation slows. The galaxy grows old. But even then, the story isn't over. The new galaxy may drift through space for billions of years before meeting another. Each collision leaves it more massive, more complex, more filled with the memories of past encounters. Galactic cannibalism is not a rare exception. It's a fundamental process in the growth of the cosmos. And while the scale of these events is almost beyond comprehension, the physics behind them is beautifully simple. Gravity draws matter together. Collisions compress gas. Pressure ignites stars. From those stars come the elements that build everything: planets, oceans, life, thought. All of it born from the friction between galaxies. When you see the Antennae, or the Tadpole, or any of the countless other colliding galaxies caught mid-embrace, you're witnessing the raw machinery of creation at work. They are the universe's forges, where destruction feeds creation, where light is born from chaos. Even our own future carries this signature. In about 4 billion years, the Milky Way will merge with Andromeda, forming a vast new galaxy. The night sky then will blaze with hundreds of billions of new stars, entire constellations redefined. From Earth, if it still exists, the spectacle will unfold in silence across the heavens. Arcs of light, streams of stars, a slow collision that lasts longer than all of human history. It's easy to think of that future with melancholy, the end of our familiar galaxy. But in truth, it will be a continuation, a next chapter, because in the universe, endings are never just endings, they are beginnings. written in gravity and time. And somewhere across the cosmos, another pair of galaxies is already taking the first slow step toward their own union. A dance choreographed billions of years in advance, performed with patience only the universe could possess. Wherever you look, creation and destruction are one and the same. The universe collides with itself, and in doing so, learns how to shine. If galactic collisions are the universe's grand feasts, then dwarf galaxies are its endless snacks. Quiet, frequent, and often invisible to casual observation, yet crucial to understanding how galaxies grow. Every large galaxy, including our own, has spent billions of years slowly consuming smaller companions. Not through dramatic crashes or blazing mergers like the antennae galaxies, but through the slow, patient pull of gravity, the same invisible hunger that rules the cosmos. This gentle form of cosmic dining is what astronomers call galactic cannibalism, and nowhere is it more evident than in the ongoing meal happening right above our heads, the Milky Way eating its smaller neighbors. The Milky Way, majestic and sprawling, seems serene when we see it painted across the night sky. But beneath that calm appearance, it's a predator in motion, a galaxy of about 200 to 400 billion stars, surrounded by a vast halo of dark matter and peppered with smaller satellite galaxies orbiting like moths around a flame. Some of these satellites have already been devoured, others are being digested as we speak. The most famous of them is the Sagittarius Dwarf Galaxy, a small faint system discovered in 1994 by astronomers Rodrigo Ibata, Jerry Gilmore, and Michael Irwin. It's located roughly 70,000 light-years from Earth and is currently being torn apart by the Milky Way's gravity. When it was first found, the Sagittarius dwarf looked like a ghost, a faint smear of stars, its structure stretched and fragmented. Over time, astronomers realized why. It was in the process of being dismantled. Our galaxy's gravity has been stripping stars from Sagittarius for billions of years, spreading them into long, looping stellar streams that wrap around the Milky Way like ribbons of light. These streams are not metaphors, they're real, measurable trails of stars, the remnants of a galaxy's skeleton stretched thin. The stars of the Sagittarius stream encircle us in a vast ring, arching through the sky, crossing the constellations of Hercules, Corona Borealis, and beyond. It's the shimmering scar of a cosmic meal still being digested. The process is slow but inevitable. The Milky Way's gravitational field is uneven, stronger near its dense central regions and weaker farther out. As Sagittarius orbits, this difference pulls harder on its near side than its far side, slowly stretching it apart. Stars at the leading edge are pulled forward, forming one stream, while those at the trailing edge fall behind, forming another. Each orbit scatters more of its mass into the halo until, eventually, the dwarf galaxy will vanish entirely, its stars becoming indistinguishable from our own. And the Sagittarius dwarf is not alone. The Milky Way is surrounded by dozens of small galaxies, tiny, dim systems that cling to the outskirts of our galactic halo. Some are still intact, like the Large Magellanic Cloud and the Small Magellanic Cloud, two bright, irregular companions visible from the southern hemisphere. They're about 160,000 and 200,000 light-years away, respectively, and even they are being slowly distorted by our galaxy's gravity. In time, they too will be absorbed. In fact, astronomers now suspect that the Magellanic Clouds are not simply passing visitors, they're part of a long-term, slow-motion merger in progress. Streams of hydrogen gas, known as the Magellanic Stream, trail behind them for more than 600,000 light-years, evidence of gravitational stripping. In cosmic terms, it's already begun. The Milky Way has started to tug at its next course. But our galaxy isn't the only one with a taste for smaller companions. The Andromeda Galaxy, our nearest large neighbor, has been feasting as well. At about 2.5 million light-years away, Andromeda is a massive spiral, larger than the Milky Way, heavier, and surrounded by its own halo of satellites. And like any mature galaxy, its halo carries the fingerprints of ancient meals. Astronomers studying Andromeda's outskirts have found vast stellar streams, enormous arcs of stars stretching tens of thousands of light-years beyond the main disk. These streams are the debris of smaller galaxies that once orbited Andromeda, only to be torn apart and assimilated. One of the most prominent is the Giant Stellar Stream, discovered in 2001. It spans nearly 300,000 light-years, curving gracefully beneath Andromeda's main disk, a remnant of a dwarf galaxy devoured billions of years ago. Using detailed simulations, researchers have traced this stream backward through time, showing how a small galaxy passed close to Andromeda's core, was shredded by tidal forces, and left behind its stars like breadcrumbs marking its final path. Some of those stars now orbit within Andromeda's halo, while others drift beyond, lost to intergalactic space. In the broader picture, Andromeda's halo is filled with such relics. Over the past decade, surveys like the Pan-Andromeda Archaeological Survey, PANDAS, have revealed more than a dozen distinct streams, shells, and arcs, each one the fossilized trace of a smaller galaxy that was torn apart. It's as if Andromeda's outer halo is a museum of galactic archaeology, every stream a fragment of history preserved in starlight. These discoveries have transformed how astronomers see galaxy formation. For a long time, we imagined galaxies forming in isolation, giant clouds of gas collapsing into stars, assembling neatly under their own gravity. But the evidence tells a different story. Galaxies grow by consuming one another. The large ones feed on the small, building themselves layer by layer over billions of years. The Milky Way and Andromeda are not exceptions. They're examples of a universal rule. This process is called hierarchical merging, and it's a cornerstone of modern cosmology. In the early universe, small galaxies formed first, clumping together like droplets of condensation on a cold window. Over time, these droplets merged, forming larger and larger systems, much like raindrops joining to make streams, streams forming rivers, and rivers merging into oceans. What we see today, the grand spirals and ellipticals scattered across the sky, are the end products of countless mergers and acts of cannibalism. But we can still see the evidence if we know where to look. Our galaxy's halo, a faint spherical cloud of stars that extends far beyond the visible disk, is full of stellar streams, remnants of galaxies that once were. Some of these streams are narrow and defined, tracing clean arcs across the sky. Others are diffuse, the ghosts of ancient mergers long since forgotten. The European Space Agency's Gaia mission, launched in 2013, has been revolutionary in revealing these patterns. By tracking the precise positions and motions of over 1.5 billion stars, Gaia has allowed astronomers to map the Milky Way in 3 dimensions and uncover its hidden scars. In 2018, data from Gaia revealed evidence of a massive ancient merger, the Gaia Enceladus event, which occurred about 10 billion years ago. Our galaxy collided with a large dwarf system, leaving behind a population of stars that still move differently from the rest, older, more metal-poor, and orbiting in a tilted pattern. Even after 10 billion years, the traces remain. The picture that emerges is one of quiet, relentless consumption. The Milky Way and Andromeda, these great spiral giants, are not static entities but mosaics, patchworks of stars from dozens of smaller galaxies stitched together by gravity. Each new meal changes their chemistry, structure, and motion. Each stream, each halo, each strange orbit tells the story of a life absorbed. And yet, despite the violence implied by the word cannibalism, there's something deeply elegant about the process. The universe doesn't waste. Every star torn from a smaller galaxy still shines, becoming part of a larger whole. What was once a dwarf galaxy orbiting independently becomes a thread in the luminous fabric of something grander. If you could step back and watch the Milky Way's evolution over billions of years, if time were sped up enough to make it visible, you'd see stars being drawn inward, long arcs wrapping around the disk like golden spirals. Each orbit would stretch and thin, forming glowing rivers of light, fading into the halo. And then gradually those rivers would dissolve, their stars scattered across the galaxy, indistinguishable from the rest. The Sagittarius stream, the Magellanic stream, the faint arcs around Andromeda, these are all temporary signatures. In a few billion years, they'll be gone, blended into the endless background of stars. But for now, we can still trace them, like faint fingerprints left behind by time. And the process will continue. The Milky Way will finish consuming Sagittarius. It will likely pull in the Magellanic Clouds, perhaps other smaller satellites as well. And then, in a few billion years, it will meet Andromeda. When that happens, all their past meals, all those stars, all those streams, will blend into one colossal new system. It's humbling to realize that our own sun orbits within this ongoing feast. Our galaxy is not a fixed structure, but a living, evolving thing. Every star in the sky, including the one we call home, is part of a story of motion, attraction, and assimilation. The universe, it seems, has only one rule: nothing stays separate forever. Every small galaxy will one day be part of a larger one. Every stream of stars will fade into the next, and every act of cosmic consumption will become, eventually, a story of creation, the quiet recycling of light into new forms. So when you look up at the Milky Way, that glowing river across the night, remember, it's not just a galaxy, it's a memory, a record of countless galaxies that came before, torn apart and reborn into something larger. A monument to the universe's appetite and its astonishing ability to turn destruction into beauty. Every galaxy, no matter how vast or serene, carries its destiny within it, and ours, the Milky Way, is no exception. For all its apparent calm, all its slow rotations and glittering symmetry, it is already on a collision course with its nearest large neighbor, the Andromeda Galaxy. A silent inevitability written into the structure of space itself. Right now, Andromeda lies about 2.5 million light-years away, visible as a faint, misty blur in the constellation of the same name. But don't let the distance fool you. It's moving toward us at about 110 kilometers per second, or roughly 68 miles per second, fast enough to cross the width of the moon in the sky in just a few decades. If only our eyes could perceive such slow motion. At that speed, the two galaxies will meet in about 4 to 5 billion years. It sounds like a long time, but in cosmic terms, it's tomorrow. By then, the sun will already be nearing the end of its stable life, swelling into a red giant as it begins to run out of hydrogen fuel. Earth, if it still exists in recognizable form, will be a very different world, possibly scorched, barren, or long abandoned by any civilization that once called it home. And yet, the sky, the great dome above whatever remains of our descendants, will tell a story of unparalleled beauty. Long before the actual merger, the first signs will appear in the heavens. Over millions of years, Andromeda will grow brighter and larger in the night sky. What now looks like a faint blur will swell into a disk of glowing light, spanning an ever-widening patch of darkness. In about 2 billion years, the view from Earth's surface, if there's still an atmosphere to see through, will be breathtaking. The Andromeda Galaxy will appear as large as the full moon, its spiral arms visible even to the naked eye, a glowing, rotating storm of billions of suns. As the two galaxies draw closer, tidal forces will begin to distort their shapes. The Milky Way's outer spiral arms will warp, and Andromeda's disk will twist as gravitational waves ripple through both systems. Long, faint streams of stars will stretch outward, connecting the two galaxies in delicate bridges of light. NASA's Hubble Space Telescope and the European Space Agency have created detailed simulations of this future event, using measurements of both galaxies' motions to predict the outcome. In those visualizations, the collision unfolds like a cosmic ballet, slow, majestic, and utterly silent. When the galaxies finally meet, their dark matter halos will merge first, followed by their disks. Stars will pass through one another, mostly unscathed, but their gravitational interactions will scramble their orbits. The night sky, once familiar, will transform into something unrecognizable. Imagine standing on some future planet, billions of years from now. Above, the sky would no longer be black and empty. It would blaze with light, swirls and arcs of starlight stretching from horizon to horizon. A panorama so vast and intricate that no horizon could contain it. It would be as if the heavens themselves had opened. When the Milky Way and Andromeda finally intersect, their central regions will pass through each other, sending shock waves of gas compression rippling outward. This will trigger enormous starburst events, where gas clouds collide and collapse, igniting millions of new stars. For a few 100 million years, the combined system will shine brighter than ever before. But this brightness will come at a cost. The structure of both galaxies will be torn apart. Their delicate spiral arms will dissolve into sprawling chaos. Tidal tails, long streams of stars, will unfurl into the darkness, some flung so far they may never return. At the heart of this cosmic dance, the two supermassive black holes, one in each galaxy's center, will spiral toward each other. The Milky Way's black hole, Sagittarius, a star, has a mass about 4 million times that of the Sun. Andromeda's central black hole is even larger, roughly 100 million solar masses. As they draw together, they'll form a binary system, orbiting one another ever closer, emitting gravitational waves that ripple through the fabric of space-time. Eventually, they'll merge in one final cataclysmic event that will release more energy than all the stars in the observable universe combined. But this energy won't be visible as light. It will pass through the cosmos as a deep, rolling vibration in space-time itself, the final heartbeat of two galaxies becoming one. Through all this, our Sun will continue its quiet orbit, though that orbit will no longer be stable or predictable. As the gravitational pull of Andromeda reshapes the Milky Way, the Sun's path may be flung outward or inward. It could be thrown into the outer halo of the merged galaxy or cast adrift between spiral remnants, far from where it began. Fortunately, the odds of the Sun, or any star, physically colliding with another star remain extremely small. Space is simply too vast. Even during a galactic merger, the average distance between stars is immense, trillions of kilometers apart. But the Sun's fate is not determined by the collision. By that time, it will already be nearing the end of its life cycle. Roughly 5 billion years from now, it will exhaust its hydrogen fuel, expand into a red giant, and eventually shed its outer layers, leaving behind a white dwarf, a dense, fading ember, roughly the size of Earth. If Earth still orbits it then, the expanding Sun will likely engulf or vaporize it long before the collision fully unfolds. So while the galactic merger is spectacular on a cosmic scale, our planet's story will have ended long before the final act. After about 2 billion years of gravitational chaos, the Milky Way and Andromeda will settle into a single, merged galaxy, a vast, smooth, elliptical system that astronomers have already nicknamed Milkomeda, or sometimes Milkdromeda. It will be larger and rounder than either of its predecessors, with a dense core and long, faint tidal streams marking the scars of its formation. Simulations suggest that the Sun, or its remnants, will end up orbiting somewhere about 100,000 light-years from the new galactic center. From that vantage point, the sky would be breathtakingly bright. Instead of a thin ribbon of stars, like our current Milky Way band, the heavens would glow with a spherical field of light, a dense golden sea of suns in every direction. Night would no longer be dark. As time goes on, Milky will grow quieter. The burst of star formation triggered by the collision will fade as gas reserves are depleted. The galaxy will age gracefully, its hot blue stars burning out, leaving behind cooler, redder populations. Eventually, it will become a tranquil, elliptical galaxy, serene and ancient, one more luminous island in an ever-expanding universe. It's tempting to imagine that no one will see this, that by the time the galaxies collide, the story of humanity will have long since faded. But perhaps not. If civilization endures, or if others arise in our place, they will witness a sky unlike any ever seen before. Imagine the astronomers of some distant future world, looking up to see two galaxies merging overhead. They would not need telescopes to understand their place in the cosmos. The evidence would be painted across the heavens. Their myths and sciences alike would be born under the glow of a universe in transformation. They might track the motion of stars across the sky, mapping the slow unfolding of the merger over millennia. They might build instruments capable of detecting the gravitational waves from the final black hole collision, recording the deep rumble of cosmic union. They might wonder, as we do now, what came before and what will come after. And if they look closely, perhaps they'll still find our traces. The remains of the solar system drifting as a quiet relic of a time long gone. Tiny frozen worlds orbiting a white dwarf star, the ghost of a civilization that once looked up and wondered about the same sky. There's something profoundly poetic about our galaxy's fate. We exist in a universe where everything, from atoms to galaxies, is drawn together by gravity's quiet persuasion. No structure is permanent. Every orbit decays. Every separation closes. The Milky Way and Andromeda are not rushing toward disaster. They are following the most natural rhythm of all, the same one that built the universe in the first place. Merging is not an end. It's continuity. Through collision, the cosmos renews itself. It's easy to think of the night sky as static, an eternal painting hung above our world. But the truth is, it's alive with motion. Even the stars we see tonight are not where they appear. Their light is already thousands of years old, and their paths are changing constantly. Our galaxy is a dance of billions of suns, and that dance is slowly bringing us home, toward Andromeda, toward union, toward transformation. Long after Milky forms, time will continue its patient work. Billions of years will pass. Stars will burn, fade, and die. New generations will form, then fade as well. And as the universe keeps expanding, faster and faster, the galaxies beyond our local group will drift away, disappearing beyond the cosmic horizon. One day, distant observers in Milky will look out into the dark and see nothing beyond their own galaxy. The rest of the universe, the great web of galaxies we see today, will have receded beyond the reach of light. It will be as if the universe has folded in on itself, leaving behind a single glowing remnant of everything that came before. But even then, gravity will still be at work, whispering through space and time. Every star, every atom, every orbit will still move to its rhythm. Because gravity doesn't end, it endures. It's the pulse of creation, and the quiet promise that even in the vast emptiness, everything is still connected. For all the beauty and chaos we can see in the universe, the glowing arcs of colliding galaxies, the newborn stars ignited in cosmic dust, the truth is, most of it is hidden. The universe we know is just a thin film of light, floating on an invisible ocean. What we call reality, everything we can observe with telescopes or detect with instruments, is only about 5% of the total universe. The rest is unseen, and the largest portion of that unseen majority, the force that sculpts galaxies and drives their mergers, is dark matter. It's an odd name for something so fundamental. Dark matter isn't dark in the way we imagine darkness. Not black, not opaque, not made of shadows. It's invisible because it doesn't interact with light or any form of electromagnetic radiation. It doesn't glow, reflect, or absorb, and yet it's there, shaping everything. It's the scaffolding on which the visible universe hangs. Astronomers first suspected its existence in the 1930s, when the Swiss astrophysicist Fritz Zwicky studied a cluster of galaxies known as the Coma cluster. He noticed that the galaxies inside it were moving far too fast. By Newtonian physics, they should have flown apart, scattering into the void. But they didn't. Something unseen, some additional mass, was holding them together. He called it dunkle materie, dark matter. Decades later, in the 1970s, American astronomer Vera Rubin provided the clearest evidence yet. She measured the rotation curves of spiral galaxies, the speed at which stars orbited their centers. If visible matter were all that existed, stars farther from the center should orbit more slowly, just as planets far from the sun move slower than those close in. But they didn't. Stars in the outer regions of galaxies were moving just as fast as those near the core, sometimes faster. The only explanation was that something massive and invisible surrounded every galaxy, providing extra gravity to hold it together. That invisible structure, what we now call a dark matter halo, dominates every galaxy in the universe. It's not just a shell around the edges, but a vast, diffuse sphere extending far beyond the visible stars, containing roughly 5 to 10 times more mass than everything luminous inside it. If galaxies are the glowing cores of lanterns, then dark matter halos are the invisible glass that gives them shape and stability. When galaxies interact, when they orbit, collide, or merge, it's not their visible parts that make first contact, it's their halos. Long before stars or gas begin to interact, their halos pass through each other, exchanging gravitational influence. It's as though two invisible clouds collide, and the light trapped within them merely follows the movement. The dynamics of galactic mergers are dictated almost entirely by these halos. As one halo passes through another, frictional effects, known as dynamical friction, cause the galaxies to lose energy and sink toward each other. Over billions of years, their dark matter halos merge, reshaping into one larger structure. Only then do the visible galaxies, the luminous disks and spirals, settle into their new form within the shared gravitational well. This invisible scaffolding determines where galaxies form, how they grow, and even how they die. Without dark matter, there would be no large-scale structure, no cosmic web. The universe would still contain gas and radiation, but it would never have clumped into the intricate network we see today. Modern cosmology has visualized this structure through massive computer simulations. Digital universes evolved according to the laws of physics and gravity. Two of the most famous are the Millennium Simulation and Illustris project, both monumental undertakings that mapped the growth of the universe from its earliest moments to the present day. The Millennium Simulation, completed in 2005, used more than 10 billion particles to represent dark matter across a cube of space, more than 2 billion light-years on a side. Each particle's motion was tracked over cosmic time, showing how matter condensed into filaments and nodes, the backbone of the universe. What emerged was breathtaking, a web-like network of thin threads connecting dense clusters with vast, empty voids between them. Galaxies, it turned out, form only at the intersections of these filaments, where dark matter accumulates most densely. In other words, Galaxies are the glowing dust trapped in the knots of the cosmic web. The illustrious simulation, published a decade later, took this even further. It added ordinary matter, gas, stars, black holes, to the dark matter framework, allowing scientists to watch galaxies evolve in astonishing detail. In these virtual universes, spiral galaxies form, collide, and merge, just as we see them in real observations. Every ripple, every distortion, every act of galactic cannibalism follows the rhythm set by dark matter. What these simulations revealed is that dark matter doesn't merely provide structure, it drives evolution. When two galaxies approach, their halos interact first, long before the visible matter does. The halos overlap and distort, pulling the galaxies closer through gravity, while at the same time heating and stirring the intergalactic gas that will one day form new stars. The halos act as gravitational nets, gathering smaller systems into larger ones, ensuring that cosmic cannibalism continues indefinitely. If you could see dark matter directly, if your eyes were sensitive to gravity instead of light, the night sky would look nothing like it does now. Instead of a few scattered points of brightness, you'd see immense glowing rivers of invisible mass stretching across space. Our Milky Way would sit inside a translucent sphere of dark matter nearly 1,000,000 light-years wide, faint but immense, like a cosmic halo of glass. And all around it, faint bridges of dark matter would connect to other halos, Andromeda, the Magellanic Clouds, smaller dwarfs, each tethered by invisible gravitational strands. In this vision, galactic cannibalism is not random chaos, but an elegant process of assembly. Smaller halos merge into larger ones, which then pull in more material, repeating endlessly. It's a hierarchy of consumption, from dwarf galaxies feeding spirals to clusters swallowing entire galaxies, all orchestrated by the gravity of dark matter. The cosmic web itself is the ultimate expression of this process. At its largest scales, the universe looks like an intricate network of filaments, with galaxies embedded along them like pearls on strings. The dense intersections where filaments meet, the nodes, are where galaxy clusters form. Over billions of years, these clusters draw in smaller galaxies through their halos, feeding the web, tightening its strands. This is galactic cannibalism on the grandest scale imaginable. Not one galaxy devouring another, but entire clusters merging into larger cosmic metropolises. Even the voids between these structures, vast expanses, tens or hundreds of millions of light-years across, exist because of dark matter. As halos form and merge in denser regions, they pull matter away from the spaces between, leaving behind enormous cosmic deserts. If you could drift into one of these voids, you would travel for hundreds of millions of years before finding another galaxy. Yet even there, faint filaments of dark matter still pass through, tenuous but unbroken. Every galaxy we see, every act of cannibalism, every merger, every birth of stars, is a localized ripple in this much larger framework. We are living inside one of these ripples, orbiting within a halo that was shaped not by the light we see, but by matter we cannot detect. Dark matter doesn't just explain structure, it also unites time. The same halos that formed in the early universe, when it was only a few 100 million years old, are the seeds of the galaxies we see today. Each collision, each merger, each faint stream of stars in our sky is the aftershock of dark matter rearranging itself. It is the slow, invisible current beneath every visible act of creation. Astronomers sometimes describe dark matter as the cosmic scaffolding, but perhaps a better word is skeleton. It gives the universe form. Without it, galaxies would never have coalesced, stars would never have found their orbits, and life, including ours, would never have had a stable place to emerge. And the story continues. As galaxies merge and cannibalize their neighbors, their dark matter halos merge too, creating even larger gravitational structures. The Milky Way and Andromeda, for instance, are each surrounded by halos extending hundreds of thousands of light-years. Halos that have already begun to touch. In some sense, the merger between the two galaxies has already started. The visible collision, the dramatic display of stars and gas, will simply be the final act of a dance that began long ago between their invisible skeletons. It's humbling to think that the forces shaping our sky are driven by something we cannot see, cannot touch, and perhaps will never directly detect. And yet, dark matter leaves its fingerprints everywhere, in the way galaxies rotate, in the bending of light around massive clusters, in the subtle ripples of the cosmic microwave background left over from the Big Bang. Every line of evidence points to the same truth, that the visible universe is only the surface of something far deeper. When we look at a photograph of colliding galaxies, we are seeing the luminous aftermath of dark matter's choreography. It's the invisible gravity beneath those swirling arms that draws them together, guides their paths, and determines their fate. Dark matter is not just part of the story of galactic cannibalism, it's the author. And so, the cosmic web grows, filament by filament, node by node, each merger feeding the next. From the smallest dwarf galaxy to the grandest cluster, everything that exists is part of this invisible structure, a universe built not by light, but by darkness. It is the silent framework of existence, the hidden geometry of creation, the unseen hand that makes the galaxies dance. At the heart of every great galaxy, there is a monster, not one of fire or fury, but of silence. An object so dense that space and time themselves bend inward around it, like fabric caught in a whirlpool. A place where gravity becomes absolute, where everything that crosses a certain boundary is lost forever. Every major galaxy harbors one of these entities, a supermassive black hole. They are the ultimate consumers, the endpoints of gravity's appetite, and in the grand drama of galactic cannibalism, they are the final act, the moment when gravity begins to eat itself. The discovery that nearly all galaxies contain these giants was one of the great revelations of the late 20th century. For decades, astronomers had seen hints, energetic radiation from the centers of distant galaxies, jets of particles shooting out at near-light speeds, and strange motions of stars orbiting invisible masses. In the 1990s, precise measurements confirmed it. Even our own Milky Way has one. At its center, in the constellation Sagittarius, lies Sagittarius A star, a black hole about 4 million times the mass of our Sun. We cannot see it directly, but we can watch its influence. Stars near the galactic center, such as one called S2, move in tight elliptical orbits around an invisible point, whipping through space at speeds over 7,000 kilometers per second, about 4,300 miles per second. Only an object of immense mass packed into a tiny region could cause that, the unmistakable signature of a black hole. These monsters are not rare. Andromeda has one too, far larger, around 100 million solar masses. Elliptical galaxies often contain black holes billions of times heavier than the Sun, some of them older than the galaxies themselves. They are not intruders, but foundations. Without them, galaxies might not exist in their current form at all. When galaxies merge, their central black holes are drawn together as well, pulled into a gravitational embrace that unfolds across billions of years. The process begins gently, as their host galaxies spiral around one another. Each black hole drags along a retinue of stars and gas, orbiting within the deep wells of their respective gravitational fields. As the galaxy's dark matter halos fuse, the two black holes are brought closer, their paths decaying through a process known as dynamical friction. the same invisible braking that slows merging galaxies themselves. Eventually, the black holes form a binary system, two invisible suns orbiting a common center of mass. Each revolution releases a little energy, not as light, but as ripples in the very fabric of space-time, gravitational waves. With every orbit, the black holes lose a tiny amount of momentum, inching closer together. Over millions of years, the orbit tightens. The ripples grow stronger, and at the end, when the two finally collide, they merge in a burst of pure gravitational energy so immense that it momentarily outshines the entire visible universe, not in brightness, but in power. This isn't theory anymore. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, made the first direct detection of gravitational waves, produced by the collision of two stellar mass black holes, far smaller than their supermassive cousins, but obeying the same rules. It was a discovery that confirmed Einstein's predictions from a century earlier and opened an entirely new window on the universe. Since then, dozens of such mergers have been recorded, each one a fleeting pulse in space-time, a chirp lasting less than a second, but carrying the story of cataclysmic union. Yet those are small by cosmic standards, the whispers of tiny black holes, each only a few times heavier than our Sun. The truly colossal ones, the supermassive black holes at galactic centers, merge on far grander scales, creating gravitational waves with periods not of seconds, but of years or even decades. Their song is not a quick burst, but a deep, continuous hum that resonates across the cosmos. In 2023, a major breakthrough came. After 15 years of observations, an international collaboration known as NanoGrav, the North American Nanohertz Observatory for Gravitational Waves, announced the first evidence of this cosmic background. By measuring the tiny irregularities in the pulses of millisecond pulsars, spinning neutron stars that act like cosmic clocks, they detected a faint, low-frequency rumble pervading the universe. It wasn't a single source, but a superposition of countless signals, the collective vibration of thousands of pairs of supermassive black holes in the process of merging across billions of light-years. The universe, it turns out, hums, and that hum is gravity itself, echoing the slow collisions of galaxies and the feasts of their central monsters. What NanoGrav detected is not the dramatic crescendo of a single event, but the background music of the cosmos. Each pair of black holes contributes a single note, low, deep, and patient, lasting millions of years. Together, they create a cosmic symphony that vibrates through space-time like the bass line of creation. It's a sound we can't hear, but one we can feel through the precise mathematics of pulsar timing. Every tiny deviation, every microsecond of difference, reveals the tremor of invisible giants locked in a gravitational waltz. These waves tell us something profound, that mergers are still happening everywhere, all the time. Even now, galaxies we'll never see are colliding, their black holes spiraling inward, warping the geometry of the universe itself. Each vibration we detect is a message from billions of years ago, the memory of a union that shaped the galaxies we see today. And yet, what happens when two supermassive black holes finally meet is still one of astrophysics' greatest mysteries. The final stage of the merger, known as the final parsec problem, is difficult to model because the black holes must shed angular momentum faster than gravity alone can account for. Some theorists believe dense gas disks help draw them together, acting as a cosmic brake. Others propose that interactions with nearby stars act as gravitational slingshots. Whatever the mechanism, once the two are within a few light years of each other, the rest is inevitable. The merger occurs in a final burst of gravitational radiation, the ultimate expression of gravity consuming gravity. And the result is not chaos, but balance. The merged black hole settles into a new state, slightly larger, slightly rounder, radiating its excess energy as gravitational waves before calming into silence again. Over time, it will continue feeding, consuming gas, stars, and unlucky clouds that stray too close, until it too becomes part of something larger. This endless sequence, black holes merging within merging galaxies, is one of the great engines of cosmic evolution. It releases unimaginable amounts of energy, stirs the intergalactic medium, and regulates the birth of new stars. Paradoxically, by swallowing matter, black holes help shape the conditions that allow galaxies to live. They are destroyers that sustain creation. Even their surroundings defy expectation. When matter falls toward a black hole, it doesn't vanish quietly. It forms an accretion disk, a swirling ring of superheated gas and dust spiraling inward at near-light speeds. The friction and compression within this disk generate temperatures of millions of degrees, releasing radiation across the electromagnetic spectrum. Some of this matter is flung outward instead of falling in, accelerated by magnetic fields into relativistic jets that can stretch for hundreds of thousands of light-years. These jets can pierce through the host galaxy, lighting up intergalactic space with streams of particles moving close to the speed of light. In the early universe, such systems were called quasars, brilliant energetic cores of young galaxies powered by ravenous black holes feeding on vast reserves of gas. At their peak, quasars could outshine entire galaxies, visible from billions of light-years away. Today, most black holes have grown quieter, their fuel supplies thinner, their jets weaker. But the hunger remains, and during galactic mergers, that hunger awakens again. When the gravitational chaos of a collision funnels fresh gas into the core, the black hole reignites, feeding furiously and reshaping the galaxy around it. In that sense, black holes are not the end of the story, but its continuation. They regulate growth, recycle energy, and sculpt the structure of the galaxies they inhabit. Without them, galaxies might grow too large or too chaotic. With them, the universe maintains its strange equilibrium, a balance between light and darkness, creation and collapse. Perhaps the most astonishing thought is that we owe our own existence in some distant way to this cosmic cannibalism. The heavy elements that make up our bodies were forged in generations of stars born from the turbulence of galactic collisions, collisions stirred and regulated by the gravitational power of black holes. The same forces that destroy also create. The same gravity that consumes also builds. And as galaxies continue to merge across the universe, their black holes will keep spiraling inward, radiating their slow, deep music into space-time. We may never hear it directly, but it is always there, a constant, inaudible hum beneath everything, the pulse of the universe itself. It's humbling to think that gravity, the simplest of all forces, becomes something so strange and elegant at its extremes. A force that begins as attraction ends as consumption. A dance that begins with galaxies ends with silence. And yet that silence, paradoxically, fills the universe with motion. Somewhere, right now, two black holes are moving closer, orbit by orbit, year by year, their mass twisting space into spirals. They will not collide in our lifetime, or in 1,000 lifetimes, but their song is already traveling through the cosmos. By the time it reaches us, it will be only a whisper, a faint vibration in the background hum of the universe. A reminder that even in darkness there is rhythm, and even in destruction there is harmony. If we could step back far enough to see the universe as a single unfolding story, we'd notice something striking. It is written in mergers. Every luminous structure, every galaxy, cluster, and filament has been shaped by collision and combination. Nothing in the cosmos remains as it began. Even beauty, in its most delicate form, is the result of cosmic violence. When galaxies meet, they do not simply destroy each other, they evolve. A spiral becomes a sphere. A disk becomes a cloud. Chaos becomes structure. It's a process so vast and slow that it's easy to forget it's happening at all. But the entire visible universe has been sculpted by these encounters, acts of gravity that transform form and order. In the grand architecture of the cosmos, this process is encoded in what astronomers call the Hubble sequence, a chart introduced by Edwin Hubble in 1926. It begins with the stately, symmetrical, elliptical galaxies, shaped like luminous eggs of stars, and extends outward to the swirling spiral galaxies, with their arms unfurled like cosmic pinwheels. At the time, Hubble imagined this sequence as an evolutionary path, a tuning fork of forms, showing how galaxies might change over time. We now know it's not a single linear path, but a dynamic story, one of cycles, interactions, and renewal. The Hubble sequence is really a snapshot of morphology, a frozen image of galaxies at different stages of a continuous transformation. Spirals, with their flattened disks and graceful arms, are younger, more active, still rich with gas and dust. They are galaxies that haven't yet endured too many collisions, but once they begin to merge, once they devour their neighbors, that ordered structure starts to dissolve. The disks buckle, the arms twist, and the galaxies puff up into more spherical forms. Stars are thrown into random orbits, and gas clouds ignite into bursts of new star formation before being consumed. When the dust settles, what remains is an elliptical galaxy, redder, rounder, older, quieter. In a sense, ellipticals are the fossils of the cosmic food chain. They are the remnants of once spiral systems that have eaten their fill and now rest in equilibrium, massive, ancient, and largely dormant. Their gas is gone, their star formation nearly extinguished, but in their quiet stillness lies the history of countless collisions, of every smaller galaxy that fell into them, of every stream of stars torn apart and absorbed. This transformation has been happening since the universe was young. In the first few billion years after the Big Bang, the cosmos was a crowded, turbulent place. Galaxies were smaller, denser, and richer in gas. The early universe was a cosmic construction zone, collisions and mergers everywhere, chaotic and relentless. The first galaxies were irregular, misshapen, like clumps of light in the darkness. Through billions of years of merging and accretion, they grew into the grand structures we see today. We often picture the universe as expanding outward peacefully, but the truth is more dynamic. While space itself expands, galaxies are gathering, clumping into filaments and nodes, guided by dark matter's invisible hand. This is hierarchical formation, the process by which small systems merge to form larger ones, and those in turn merge into even larger structures. Every galaxy is the result of billions of years of assembly. Each one is a history book written in gravitational scars. Simulations like Illustris and Eagle have recreated this entire history in digital form. They show the early universe as a glowing mist, gradually coalescing into dense filaments. Tiny proto-galaxies collide, merge, and form more massive systems. Starburst after starburst lights up the darkness. The galaxies that survive the stormiest era of mergers, around 10 to 11 billion years ago, go on to become the great ellipticals that now dominate the centers of galaxy clusters. By contrast, spirals like our Milky Way live in quieter neighborhoods, where mergers are less frequent and more gentle. That's why their structure remains intact, for now. But their fates are sealed all the same. Given enough time, even the most graceful spiral will collide, merge, and settle into the same elliptical destiny. So, in a cosmic sense, the Hubble sequence isn't a classification of galaxy types. It's a record of time. Spirals represent youth and vitality, full of star formation and motion. Ellipticals represent age and memory, the final smoothed-out remnants of countless acts of cosmic consumption. Between them lies everything, The transitional shapes, the warped systems, the tidal tails and luminous bridges that connect one form to another. The transformation from spiral to elliptical is a form of cosmic alchemy. Gravity takes order and turns it into chaos, then into equilibrium. Each merger redistributes energy, angular momentum, and matter, erasing sharp edges and creating something new. Even the colors of galaxies tell this story. Blue for youth and creation, red for age and repose. In the long view, it's all one continuous motion, a cycle of building, devouring, and resting. It's tempting to see these collisions as acts of destruction, but that's only a matter of scale. From within a single star system, the merging of galaxies would seem catastrophic. Gravitational tides stretching orbits, clouds of gas collapsing into supernovae, skies filled with shifting constellations. But from the universe's perspective, its creation, each merger redistributes the raw material of existence, generating the diversity of forms we see today. This is creative violence, the paradox at the heart of cosmic evolution. The same gravitational hunger that tears galaxies apart also makes them more complex, more massive, more enduring. The universe doesn't build gently. It builds through collision, compression, and change. It builds by consuming itself. Every time two galaxies merge, new stars are born, black holes awaken, and elements are forged. The aftermath of every collision becomes the foundation for the next. Over billions of years, the result is not ruin, but refinement. A universe that continually recycles its matter into new shapes, new light, new beginnings. If we could watch it all unfold in time-lapse, billions of years condensed into minutes, we would see the universe shimmer with motion. Galaxies colliding, merging, fading into one another. Bright blue spirals twisting into hazy red ovals. The cosmic web pulsing with light, growing ever more intricate, ever more interconnected. And through it all, gravity would be the conductor, patient, tireless, endlessly orchestrating the same theme in infinite variation. In the end, galactic cannibalism is not a story of destruction at all. It's the story of growth, of evolution through interaction, of the universe learning how to create beauty through force. Everything we see, from the Milky Way's spiral arms to the elliptical giants at the centers of clusters, exists because of this balance between chaos and order, violence and grace. The universe, it seems, doesn't shy away from its hunger. It embraces it, because from that hunger, everything beautiful is born. The universe is not a place of peace, not really. It only appears that way because we live inside its still frames, inside moments too brief to feel its motion. But behind the calm of starlight, there is endless change, a quiet storm that never ends. Galaxies collide and devour one another. Stars live, die, and seed the next generation. Black holes merge, and space itself ripples with the echoes. Even the light that reaches us is recycled, energy born from ancient collisions, carried across billions of years just to touch our eyes for a fleeting instant. Creation, in the universe, always begins with destruction. The same gravity that tears galaxies apart also binds them closer. The same explosions that end a star's life forge the elements of new worlds. The same entropy that dissolves order gives rise to complexity. It's not a contradiction. It's a rhythm, a law as old as time itself. If life mirrors the cosmos, perhaps this is its greatest lesson, that endings and beginnings are the same event seen from opposite directions. Everything we are, every atom in our bodies, was once part of something that died, something that fell, something that burned. We are the recycled ash of stars, the dust of galaxies that merged and reformed, the quiet inheritance of cosmic hunger. And somewhere, right now, another merger is beginning. Two galaxies drifting together across the void, slowly folding into one. Billions of years from now, The light from that collision will reach some distant world, and someone there might look up and wonder where it came from. The cycle will continue. Creation, destruction, rebirth, the eternal heartbeat of the universe. So as you look up tonight, remember this: the stars you see are not eternal. They are the children of wreckage, born from the remnants of ancient cosmic collisions, from galaxies that lived, died, and were reborn into light. Their calm glow is not a promise of permanence, but a whisper of change. And in that change, the universe finds its beauty, a beauty that consumes itself, and in doing so, becomes infinite.